Hello, welcome back. Today we're going to be talking about series and sigma notation. We've been talking about sequences in which we have an ordered list of elements. When we talk about a series, we're talking about taking that list of elements and adding them up. 4 plus 2 plus 1 plus a half plus a quarter plus ... A series can either be finite, in which we have a finite number of terms. A finite series always adds up to some particular value. In this case, 10 plus 13 plus ... plus 109 equals 2023. Or a series can be infinite, in which there are infinitely many terms that we're trying to add up. An infinite series doesn't always have a value that it adds up to. Some infinite series do have a value. Some infinite series have a value, but can have a different value depending on how you organize the terms. And some series just don't have a value at all. If you keep adding infinitely many ones together, you don't get an answer. Now that's the idea of convergence and is covered in a class like calculus or analysis. So when you have a finite or infinite series where the terms are written out with a ... what we'd like to do is we'd like to write this series in a more compact and precise form without these ellipses. So to do that, we're going to use something called sigma notation. And that looks like this. We're going to break this down carefully shortly, but before we do that, I'd like to take a moment to translate this notation into English. The way you should approach this is to read in this direction. We should read this notation as the sum from k equals m to k equals n of a sub k. So let's make sure we understand what this means. First, when you see a sigma, this is a capital sigma, when you see a sigma, that denotes that we're going to be summing things together. This k down here is telling us that we're going to use k as an index. This m here is telling us the first value of the index in the series. This n corresponds to the last value of the index in the series. And whatever comes after the sigma sign is an expression for the kth term in the series. So when we see a sub m plus a sub m plus 1 plus ... plus a sub n, we're seeing that every single term in that series looks like a sub something, where that something starts off at m and ends with n. Let's practice interpreting an expression written in sigma notation. Let's look at this example. We need to identify each of the parts of the sigma notation and substitute appropriate values of the indexing variable. We recognize that the indexing variable here is k. That's the variable below the sigma sign. Now let's look to see what comes after the sigma sign. This is telling us that the formula for the kth term is k plus 1 over k plus 3. Now let's read and find the first value of k. That's 6, that's below the sigma sign. And the last value of the index is when k is 15. So now what we do is we take this information and we line up our sum. We see that k starts out at 6 and increases up until 15. Then, for each of these values of k, we plug that into the formula. We see 6 plus 1 over 6 plus 3, 7 plus 1 over 7 plus 3, 8 plus 1 over 8 plus 3, etc., up until 15 plus 1 over 15 plus 3. Simplifying these expressions, we see 7 over 9 plus 8 over 10 plus 9 over 11 plus ... plus 16 over 18. And this would be the way to convert the sigma notation into a sum involving plus signs. That's it for now. See you soon.